The Earth begins not with silence but with motion, not with form but with heat. Suspended in the dark vacuum of space, the young planet turns slowly its surface incandescent churning, like the skin of a star that has lost its way. There is no land, no ocean, no sky. Only a seething sphere of magma wrapped in a thin veil of superheated vapor, glowing orange-red beneath the distant indifferent stars. From within the mantle folds and flows, cycling molten silicates with a rhythm older than time. The newborn Earth is still digesting itself, still swallowing the last fragments of its own formation, still accreting pieces of its identity from the debris left by the birth of the solar system. Microscopic dust has fused into mountain-sized planetesimals. These in turn have collided and fused again, a cascade of coalescence that leads to this moment a planet-sized ember just barely beginning to breathe. The surface is unstable, alive with upwellings of fire and the descent of heavier elements. No shell can form and hold, no crust can last longer than the next burst of convection or rain of iron-rich rock. Above a temporary atmosphere of silicate vapor hovers composed not of water or air, but of atoms torn from rock by unbearable heat. Silicon, magnesium, sodium, all evaporated into gas, and swirling overhead like ghosts of mountains that will one day rise but have not yet been imagined. The temperature of the Earth at this stage is not metaphorically hot but literally incandescent. At more than 2,000 degrees Celsius, even minerals with the highest melting points remain fluid, and even the sky seems to burn. There is a softness to this fire, though, if one looks slowly enough. The molten mantle moves not in chaos, but in currents, great planetary circulations as wide as continents and as deep as oceans. These are not violent. They are methodical, patient, unceasing. Plumes rise not with fury, but with inevitability. Lava does not boil, it flows like breath. It takes 1 billion years for the Earth to begin cooling in any meaningful way. 1 billion years to exhale. And still, the fire does not leave. It simply begins to rearrange itself. Here in this first act of planetary identity differentiation begins. Heavier elements sink, lighter ones rise. The beginnings of structure emerge from this thermal chaos, not in the form of stability, but in the quiet beginnings of layering. The surface will remain chaotic, but below slow patterns begin to assert themselves. Iron drifts downward toward what will become the core, drawn not by will but by density. Silica and alumina migrate upward, laying the groundwork for the future crust. It is a silent process, this separation, yet it will determine the character of the Earth forever. Without it there would be no continents, no oceans, no atmosphere, only a homogeneous sphere, blank and still. Yet nothing about the young Earth is still. It is not a place of rest, but of restless transformation. Even the planetary shape wavers at the edges, slightly ablate from its rotation, wobbling in its early spin like a slowing top. The sun, newly ignited, bathes the molten planet in light that is largely irrelevant, for this heat comes not from above but from within. Residual energy from the planet's formation combined with the constant influx of kinetic force from accreting debris. Each impact delivers not just mass but fire kinetic energy transformed instantly into heat. A single large collision can raise global temperatures by hundreds of degrees, and so the surface remains molten not despite cooling, but because the sky keeps falling. The moon not yet born waits in potential. It will emerge soon, perhaps violently, perhaps slowly. The records are sparse, lost beneath the crustless churn of time. What is known is that Earth's earliest days are marked not by silence, but by continual exchange. Fire is the first language the Earth speaks, not in words, but in flows, in gradients, in the tireless rearrangement of matter under pressure. The planet breathes fire, not metaphorically, literally, And yet there are quiet ironies even here. For all its violence, the early Earth is in a sense at peace. No storms rage, for there is no weather. No earthquakes fracture, for there are no plates. No oceans swell, for there is no water. It is a world of pure geology, unshaped, unburdened by biology or climate. Just heat, gravity, and time. Only took a few 100 million years to arrive at the simplicity. Only took a solar system to melt down enough material for a glowing sphere. Only took everything that came before to make a place with nothing on it yet. And yet in that nothing there is everything. All later complexity rests on this foundation of fire, on this early dance of pressure, density, and temperature. The first breath of a planet is not air, but heat. The first weather system is not cloud, but convection. The first surface is not land, but liquid stone. Somewhere deep beneath that surface patterns are forming. They are slow. They are silent. They are irreversible. They do not yet look like continents, but they will. They do not yet host life, but they will. For now, the Earth is a thought still forming a planet caught in the act of becoming. The fire rules everything, but it does not rage. It moves. It waits. It knows nothing of biology or erosion or tectonics. It only knows motion and heat. That is enough for now. Above the molten earth, clouds swirl not with water but with vaporized rock. They rise, condense, and fall again in endless cycles of futility. This is not rain as we know it. These are not droplets, but droplets of silicate magnesium and sodium minerals flash boiled into gas by surface temperatures exceeding 2000 degrees, only to recondense into a molten drizzle that evaporates again before it can settle. It is a rain of fire, a rain that never cools a downward motion without arrival. The sky is thick with it, a hazy cauldron of airborne stone that flickers in the reddish light of the infant sun. From afar, Earth would look like a glowing orb, wrapped in a gauze of smoke pulsing with slow convection, and wrapped in a temporary atmosphere made not of air but of rock turned ephemeral by heat. This mineral rain falls endlessly, but never with success. Each droplet attempts to lower the planet's fever, but the ground itself betrays the effort. There is no solid surface to receive it. The crust cannot yet form, and if it tries, it melts again. Cooling is not linear. The early Earth is still fed by internal heat from radioactive decay, from gravitational differentiation, and from the ceaseless bombardment of solar leftovers. Each falling object, even the smallest, adds its own flash of warmth, briefly undoing hours or centuries of slow temperature loss. In this way, fire defends its reign not with drama but with quiet persistence. It takes energy to escape energy. Cooling takes more than time. It takes luck, and the Earth has none of it yet. The early atmosphere, such as it is, clings to the planet in a tenuous grip. There is no oxygen here, no nitrogen-rich wind, only a thick brew of outgassed volatiles. Carbon dioxide, sulfur, dioxide, hydrogen, water vapor. Though the water cannot condense, it floats as steam in a sky too hot to allow it to fall. This superheated shroud is dense and opaque, hiding the planet's glow from space, trapping its heat, like a velvet curtain that never lifts. Lightning flickers through the clouds, but not in familiar ways. These are sparks not of weather, but of planetary frustration, static, built from rising plumes of metal-rich gas discharges that dance across the upper layers of a sky that breathes rock and exhales flame. This is the age of incomplete transitions. Every process begins but cannot yet conclude. Rain that cannot fall, crust that cannot hold, oceans that cannot form. It is a world suspended between states, between chaos and order, between fluid and solid, between heat and the memory of what cold might one day mean. Nothing yet resembles the world to come, and yet every motion here lays its foundation. Each failed raindrop carries a trace of future hydrology, Each temporary surface leaves behind patterns of convection that will eons from now become the engine of tectonic drift. Even in its refusal to cool, the Earth is preparing, not because it plans, but because entropy is patient. And yet there is mystery in this refusal. Cooling should be inevitable. Over time, heat should radiate away into the vacuum of space, yet something delays it. Scientists debate the exact mechanisms. Was it the density of the atmosphere rich in greenhouse gases before there were even plants to produce them? Was it the frequency and scale of bombardment, constantly reheating the crust from above? Was it the radioactive decay of early isotopes hotter and more abundant than those that remain today? Each answer is partial, each leaves a question. Why did the Earth take so long to cool compared to its rocky siblings? Why did Mars lose its heat so quickly and the Moon even faster? Was it sheer mass that kept the Earth molten longer, or some deeper choreography of elemental balance and kinetic timing? The truth lingers beneath our feet, but it does not speak clearly. Even now, much of this early history is inferred, not observed. The rocks that could tell us most have been recycled, subducted, melted, and born anew 1,000 times. Only whispers remain isotopic ratios in ancient zircons, patterns in mantle composition craters half erased by time. The Earth guards its memories in motion, not in monuments. Still, some ironies survive. It is not the largest impacts that define this age, but the constant drizzle of failure. 1 billion years of rain that never lands. A sky full of rocks that tried to become land again only to return to vapour. Only took 500 million years for a single droplet to survive its fall. Only took the slow cooling of a planet's breath to make puddles possible. Only took a universe full of stars for one stone sphere to figure out how to sweat. And when at last the first true raindrop falls and stays, when one silicate grain does not melt but merely rests, it will not announce itself. There will be no instant change, no sudden shift. The crust will still be fragile, the atmosphere still thick. But it will mark a turn, a pivot so quiet it cannot be heard. The world begins to cool not with a storm but with a sigh. The fire remains, but it begins to contract, to descend, to withdraw. The surface starts to think about becoming surface. Not yet, not for millions more years, but the thought has entered the stone. Above the rain still falls, below the mantle still boils. Between them the Earth persists in its refusal to resolve a planet not quite finished, not quite stable, not quite real. But it is becoming, slowly, inevitably. It is learning how to cool and how to hold on to what it cools, and in that balance it is learning how to become a world. Deep beneath the molten oceans of the early Earth, heavier elements begin to descend. This is not a fall in the ordinary sense, not a tumble through open space, but a slow, irreversible inward drift, a surrender to density. Iron, nickel, and other metals that cannot float in silicate seas begin to move downward, drawn not by choice, but by their very nature. They migrate through a magma mantle that resists and yields at once, weaving long paths of descent that carve the planet's first internal architecture. It is a silent rearrangement, not violent, but thorough. Over millions of years, the Earth begins to sort itself from the inside out, trading chaos for stratification, letting gravity sculpt identity from entropy. The process is not visible from the surface, not marked by firestorms or eruptions, but its effects will echo through every later age. This is the moment when the core begins. It starts as a slow concentration iron atoms gathering, clustering, nudging one another inward. But as the metallic migration deepens, the consequences become profound. As the heavy elements pool at the planet's center, the energy released is immense. Gravitational potential transforms into heat. The very act of separation warms the Earth again, fueling further convection in the mantle. and preserving the outer world in its molten state. Fire, it turns out, is self-sustaining, fed by the architecture it enables. As the core forms, the outer layers are stirred anew. Fire reinforces fire. The planet is still cooling in theory, but in practice it blazes on. Eventually, the sinking metals reach a threshold where pressure and temperature converge to force a new kind of transformation. The inner core begins to solidify, even as the outer core remains molten. Crystalline iron forms at the center of the planet, dense and orderly, locked in a lattice by pressures too immense to imagine. Around it, the liquid iron of the outer core churns in slow spirals sheared by planetary rotation and driven by the lingering heat of formation. In this layered inferno, something extraordinary emerges, not a substance but a field. The geodynamo is born. No one sees it, no one feels it, but its presence reshapes the Earth's destiny. A magnetic field, weak at first but growing stronger, begins to stretch outward from the molten depths, wrapping the planet in invisible threads of force. This magnetic cocoon will not shield the surface from heat or fire, but it will matter deeply to what comes later. It will one day deflect solar wind, preserve atmospheres, guide migratory animals, and record reversals in basalt flows. For now, though, it simply hums. A quiet pulse, a planetary murmur that says the core is here. It does not yet influence daily conditions on the surface. There is no biosphere to protect, no compass to align, but it is foundational. In time, it will matter more than anyone can imagine. And yet even this process of differentiation contains its questions. Why did the core form so early and so thoroughly? Was it triggered by a single event, a moon-forming impact that melted the planet so deeply it forced segregation? Or was it gradual, a product of steady inward migration over eons? Some models suggest rapid core formation perhaps within a few million years. Others point to slower processes, more complex flows of partial melting and chemical equilibration. We cannot know for certain. The clues are locked in isotopic signatures in trace elements preserved in minerals older than any known rock, and many of those signatures are ambiguous. There are hints, but few answers. The center of the Earth, paradoxically, is both essential and hidden. Its story inferred rather than witnessed, its timeline veiled in uncertainty. Still some ironies rise with the metal. It is this downward movement, this quiet gravitational sorting that gives the planet its heartbeat. Without it, there would be no magnetic field, no inner layering, no tectonic motion as we know it. Only took a few billion tons of iron deciding not to float. Only took gravity doing what gravity always does. Only took a planet saying, "Let the heavy things fall." And yet the core's awakening is not the end of anything. It is the beginning of balance. The Earth becomes not just a hot sphere, but a structured one, a planet with zones, with gradients, with hidden interiors that shape surface futures. Heat moves outward now through defined layers. Pressure increases in predictable ways, and though everything still flows, the flows gain pattern, rhythm, expectation. The Earth's insides begin to speak a language that can be followed, traced, charted. Not by humans, not yet, but by the elements themselves, by the currents and gradients that now have something to push against. On the surface, not much has changed. The magma oceans still heave. The rain of rock still evaporates before it lands. The sky still glows with vaporized stone, but underneath the world has begun to settle into its own gravity. It is no longer just a ball of molten matter. It is becoming a system, a planet with inside and outside, with depth and direction. The future is beginning to stratify. In time, this layering will allow crust to form and survive. In time, the presence of a stable core will protect the atmosphere and regulate the surface temperature. But that is far off. For now, the Earth remains incandescent. Its fire is not retreating, but reorganizing. The planet is not cooling so much as learning how to store its heat. Fire goes inward now. It hides in the mantle, in the outer core, in the residual decay of isotopes that still hum with energy. It no longer needs to erupt constantly. It has found compartments, and in those compartments, fire waits. Above, clouds still boil with metallic fog. Below the mantle shivers with slow convective breath, and at the very centre a sphere of solid iron turns ever so slightly wrapped in a sea of molten metal that turns with it differently. That motion, imperceptible though it is, will define the planet's magnetic rhythm for billions of years. It will guide particles, draw auroras, shield oceans not yet born. It is not dramatic, but it is profound. The Earth has a core now, and though nothing on the surface betrays that truth, the planet is forever changed. Amid the endless churn of magma, fleeting structures begin to rise unstable, fractured rafts of solidifying silicate that briefly float upon the surface like foam on a boiling pot. These early crustal fragments are thin, brittle, and ephemeral. They crack and founder as soon as they form, reabsorbed by the restless mantle beneath. The heat is still too great, the convection too vigorous. What tries to become land is swiftly undone, and yet the attempt repeats. Over and over, for millions of years, the planet tries to harden a skin, a fragile exoskeleton, over a still molten heart and fails. The Earth is learning how to crust, but the lesson is long, and the teacher is fire. These protocrusts differ from modern continents in almost every way. They are mafic dense and dark, rich in magnesium and iron, more akin to basaltic ocean floor than granite mountains. There is no buoyancy to keep them aloft. Their chemistry betrays them to gravity, and as soon as they fracture, they are dragged downward, recycled into the mantle that bore them. This cycle of creation and destruction is not yet plate tectonics, not as we know it, but it is its slow rehearsal. The Earth is experimenting with surface mobility, improvising with temperature and pressure gradients, exploring what it means to have a top and a bottom. From above, if one could observe through the thick, vaporous atmosphere, the surface would appear patchy, glimmering sheets of dark rock adrift on oceans of lava, their edges glowing with fresh melt, their centres cooling only slightly before collapsing again. Cracks form across them like fractures in drying clay, but on a planetary scale. Some of these slivers may last decades, others mere hours. It is a surface, in quotation marks, a placeholder more than a boundary. It cannot yet support weight because there is no weight to support. No atmosphere to press down, no ocean to press back, no biosphere to mark a difference between above and below. Only fire and failed experiments in solidity, and yet these failures are not wasted. Each collapse stirs the mantle anew, remixing chemical layers and setting in motion gradients that will matter for future convection. Each destruction leaves behind a legacy zircon grains, trapped in melt oxygen isotopes, altered by brief exposure to an exosphere. The clues are subtle, scattered, but they remain. Billions of years later, geologists will find them embedded in younger rocks, tiny time capsules from a surface that never quite was. Their presence whispers of an Earth trying to differentiate, to find structural meaning in chaos. Still, the mystery endures. What made the crust finally stabilize? What changed in the balance between internal heat and surface loss, between mantle buoyancy and gravitational pull? Some theories suggest a gradual thinning of the atmosphere allowed more efficient radiative cooling. Others propose that enough radioactive elements had decayed to lower the planet's internal heat budget. Still others point to chemical evolution in the mantle, a slow depletion of fusible elements that reduced volcanic outpourings. None of these answers fully satisfies. Perhaps it was all of them overlapping like lava flows on a fractured plane. Or perhaps the crust simply got lucky. There is irony in that a process so central to planetary evolution may have hinged on coincidence. Only took 1 billion years of trying. Only took every atom being in the wrong place at the right time. Only took a planet's refusal to stop attempting solidity. The modern crust-stable layered home to mountains and rivers will one day owe its origin to this long epoch of impermanence, to the crusts that did not last, to the fragments that cracked, folded, and fell back into fire. This is the quiet paradox of geology. What remains is shaped by what disappeared. And so the Earth's first crusts are not foundation stones, but test drafts. They mark a planet in rehearsal, refining its choreography of density and pressure, cooling and convection. There is no audience yet, no witness. But the performance continues. Meanwhile, the mantle remains in motion, pushing up plumes of melt that fracture what little crust there is. These upwellings rise like slow fingers from the deep-forming domes that crack the surface into floating plates. Not tectonic in the modern sense, but an echo of what will come. Slabs of rock move horizontally for short distances before subducting, pulled back down by their own weight. There's no direction, no system, just circulation, but circulation is enough to matter. It defines how heat escapes, how chemical gradients shift, how the surface evolves. The Earth does not yet have continents, but it has begun to draw the blueprint. Above all of this, the atmosphere continues its quiet brooding. It thickens with volcanic gases, carbon dioxide, water vapor, sulfur compounds, each outgassed from the mantle through fractures in the proto-crust. These emissions rise cool slightly and linger, still too hot for condensation, too dense for escape. But they are beginning to accumulate, and that accumulation will matter. It will one day trap heat more efficiently, then slowly allow it to dissipate as the balance shifts. The sky is still not blue, it is grey-red, sulphurous, but it is no longer nothing. It is part of the system now. On the ground, if such a term can yet apply, each new surface becomes a record. Not in permanence, but in process. A map of failure perhaps, but a map nonetheless. The Earth's earliest crusts are like sketches in molten charcoal drawn and erased by the same hand. Still they leave behind memory, they shape the next attempt, they are not wasted. Even now, beneath modern continents and oceans, the echoes of these early crusts persist. Traces in deep mantle plumes, anomalies in seismic waves, minute variations in elemental abundance. The Earth remembers not in visible scars but in patterns, and those patterns begin here in a crust that cannot hold but cannot stop trying. Across the vast reaches of the early solar system, countless fragments of stone and ice still wander, the relics of formation, the debris of ambition unfulfilled. These are the leftovers of planet building, the pieces that never found a home, and now gravity brings them back. One by one, and then by the million, they fall toward the glowing Earth, pulled by its mass, its heat, its presence. They come in waves, in swarms, in centuries-long drizzles of destruction. This is the late heavy bombardment, not a moment but an era, not a single catastrophe, but a rain of them sustained and merciless, stretching across hundreds of millions of years. The Earth, already restless with fire, is now under siege from the sky. Each impact carries energy far beyond comprehension. Even small objects only kilometers across arrive with explosive force, vaporizing upon contact, melting vast stretches of crust, excavating basins, and injecting shock waves deep into the mantle. Larger impactors, dozens or hundreds of kilometers wide, reshape continents that do not yet exist. They do not merely scar the surface, they reset it. Whatever early crust survives is shattered, melted, dispersed into plumes of ejecta that arc high into the sky, then rain down as incandescent ash. The air thick with vaporized rock and sulfur glows with each new arrival. The sky is not a refuge, but a threat. Fire rains from above, even as it stirs from below. There is no direction that does not burn. The reasons for this bombardment are rooted in the architecture of the solar system itself. Giant planets, especially Jupiter and Saturn, shift subtly in their orbits, destabilizing the asteroid belts and outer reservoirs of debris. These gravitational adjustments fling planetesimals inward, transforming what was once distant and cold into a cascade of heat and violence. Earth becomes a target not because of its nature, but because of its location, a middle child in a turbulent system. And so the impacts continue not out of malice, but out of motion. A planetary lottery played with no intention, only inertia. What survives these collisions is not land, but memory. Buried within ancient minerals are isotopic clues, signatures of impact heating, traces of pressure regimes that could only arise from sudden immense force. Zircons in the Jack Hills of Australia, some more than 4.3 billion years old, carry whispers of this era, their oxygen isotopes hinting at the presence of crust and perhaps even water before the worst of the bombardment. These zircons are not fragments of land, but of processed mineral testaments to an Earth already struggling towards stability, even as the sky denies it. And yet the ironies persist. For all its devastation, the bombardment may have been a necessity. Some scientists propose that these impacts helped stir and recycle the mantle, accelerating chemical differentiation. Others suggest that volatile-rich impactors delivered key ingredients, water, carbon, nitrogen, that would later support life. There is no consensus, only layered possibility. It may be that Earth needed to be broken to become whole. Only took a solar system to build a planet. Only took the ruin of a crust to make way for another. Only took a few billion collisions to set the stage for quiet. Amid this destruction, the mantle continues its dance. Plumes rise beneath the bombardment, indifferent to the chaos above. Some impacts pierce so deeply that they trigger new volcanism, creating feedback loops between sky and stone. Others leave behind basins that will later become cradles for oceans once water finds its way to the surface. Even the largest craters are not permanent. The planet heals itself not with kindness but with heat. Melt fills the voids. Convection erases the scars. In time the surface forgets, but the deep earth remembers. Still, the bombardment raises enduring questions. Why did it occur so long after planetary formation was thought to be complete? What exact mechanisms triggered the destabilization of these distant bodies? Some models point to a shifting resonance between Jupiter and Saturn, a small change with massive consequences. Others challenge the very existence of the late heavy bombardment as a discrete event, suggesting instead a gradual decline in impacts that has been misunderstood due to a lack of surviving rocks. The Moon, less geologically active, preserves more craters its surface, a map of violence, while Earth's is a palimpsest written over again and again by fire and time. And yet there is a quiet poetry in this rain of stone. It is the last great cleansing, the final refusal of simplicity. Once the bombardment wanes, the Earth will never again face such a universal assault. From then on, change will come more slowly, more intricately shaped by internal forces, by water, by the long ambitions of chemistry and chance. But during this epoch, the planet is made and unmade by the cosmos itself, shaped not by its own will but by the residue of others. The skies gradually clear. The impacts grow fewer, the intervals between them longer. The crust, though still fragile, is given time to settle. Volcanism continues, but its rhythms begin to localize. The heat is still immense, the atmosphere still toxic, but there is a lull, a pause, a moment in which the surface begins to remember its own shape. A world once entirely without reprieve now experiences the novelty of survival. Even here, the planet's deepest future is foreshadowed. Impact basins will guide future continental boundaries. Crust melted and remade will host the first signs of tectonic mobility. Gases released in these collisions will feed the primitive atmosphere that one day shapes weather. Nothing is wasted, nothing is final. The Earth has endured its storm of stones, and while the scars may not remain, their consequences echo through every layer of what follows. Beneath the crust, fractured, partial, and often transient, lies a deeper, older force. The mantle, vast and viscous, continues its slow circulation, a planetary interior in constant motion. It churns not with the chaos of firestorms, but with the patience of heat trapped in stone, with the residual breath of a planet still exhaling its formation. This movement is driven by gradients of temperature and density, by the tireless climb of hot material rising, and the corresponding descent of cooler remnants above. The result is convection slow and immense, invisible from the surface yet foundational to everything that follows. The mantle is not content to remain still. It rebels in silence, in heat, in movement that takes millions of years to cross 1,000 kilometers, a kind of geological protest against stasis. This rebellion is not symmetrical. It is shaped by uneven cooling, by chemical differentiation, by hidden structures inherited from early Earth's molten chaos. Some regions rise in vast plumes, domes of superheated rock pushing toward the surface with steady force. Others sink in quiet descent, cooled and densified by the burden of repeated bombardment, or by temporary crustal fragments dragged downward by gravity. The mantle begins to develop patterns, not rigid, not fixed, but rhythmic enough to influence the surface above. It does not form tectonic plates yet, but it starts to think in those terms. Thermal boundaries emerge. Convective cells expand and fold. The lithosphere, such as it is, becomes a passive passenger on these internal waves. Fire is no longer everywhere. It moves in corridors, in cycles, in circulations that will shape the deep Earth for billions of years. In some regions, upwelling plumes break through the thinning crust, forming massive volcanic outpourings. These are not isolated eruptions, but planetary-scale lava floods flood basalts that cover hundreds of thousands of square kilometers in sheets of molten rock. The Earth does not erupt in fits and starts. It breathes magma in slow heaves. Some of these outpourings last for 1 million years or more. There are no witnesses, no sound, but the hiss of rock against rock, yet the consequences are lasting. These flows bury early surface compositions, overwrite craters, reshape the balance of volatiles in the atmosphere, and with each outpouring the mantle loses a little more of its heat. Slowly it moves from rebellion to rhythm. Even now, the inner workings of mantle convection remain only partially understood. We can model it, trace it through seismic waves, map its echoes in the chemical fingerprints of igneous rocks, but we cannot see it directly. We infer its loops and patterns from what appears above, like watching shadows to guess the shape of wind. Questions linger. Are there stable superplumes that persist across eons rooted deep in the lower mantle? How many convection cells span the Earth's interior? 2 layered vertically, or many stacked and sheared over time? What are the roles of ancient subducted slabs long since consumed, now embedded in the lower mantle like ghosts of lost tectonics? These mysteries are part of the Earth's silence, a deep history told without words, stored in the motion of minerals under pressure. And yet mantle convection is the engine of transformation. It powers volcanism, enables eventual plate tectonics, circulates heat, and drives the chemical differentiation that makes continents and oceans possible. Only took 4 billion years to build a conveyor belt. Only took the planet's refusal to sit still. Only took the restless sigh of trapped fire rising inch by inch, year by year, until continents could one day drift. There is an irony too in the mantle's concealment. It is the most massive part of the planet, more than 2/3 of Earth's volume, and yet we know it least. The crust so thin and temporary holds the surface memory, while the mantle vast and ancient moves in secret. It is too deep for direct access, too hot for permanence, too fluid for records. But it carries within it the scars of every phase change, every subducted fragment, every outgassed bubble of primordial atmosphere. It remembers not with layers, but with motion. Above the crust begins to stabilize in patches held between zones of intense upwelling. Between volcanic provinces it thickens slightly, resisting melt long enough to accumulate trace minerals to host pockets of cooler temperatures. In these zones, early differentiation of the crust may begin the quiet accumulation of more felsic materials, lighter in colour, and composition subtly altering the future buoyancy of land. It is a minor change, a delicate shift in chemistry, but it matters. Over time, these differences will build the contrast between oceanic and continental lithosphere, a contrast that underpins all later surface architecture. Even the atmosphere begins to feel the effects. As volcanic outgassing continues and as the surface gradually stabilizes, greenhouse gases accumulate in greater quantities. Carbon dioxide, water vapor, methane all continue to thicken the planet's shroud. But some of the most violent gases like hydrogen sulfide and ammonia begin to dissipate. The air remains hostile, thick, hot, and toxic, but it is changing. It is becoming layered, structured, possibly even starting to lose heat more efficiently to space. The Earth is still a fire world, but it is no longer a firestorm. There are zones of quiet now, of comparative calm places where heat seeps out more slowly and where the future might take root. Still, the rebellion continues. The mantle is not finished. It will never truly be. Beneath the crust, the planet continues to churn, to pull itself apart and rebuild, to carry its own heat outward in cycles that span millions of years. This is the rhythm of a living planet, not in the biological sense, not yet, but in the structural one. It breathes with silicate lungs. It circulates in molten loops. It reshapes itself from the inside out, without rest, without intention, without pause. And above all this, the crust remains thin, fragile, experimental. A membrane, not a shield. A suggestion of surface, not yet a promise. But it is enough to hold volcanic plains, to preserve isotopic traces, to mark the beginning of stability in the shadow of motion. The mantle still rebels, but now the crust begins to listen. The Earth's surface, though still precarious, begins to display forms more complex than fractured crust and molten plains. Volcanic provinces swell and spread, rising in irregular swells across the partially solidified lithosphere. These are not discrete mountains, but vast fields of fire, seas of lava that roll outward from central vents in slow, unstoppable tides. The scale is planetary. One eruption can last thousands of years, covering regions the size of modern continents in successive waves of basalt. Between the flows, vents collapse, forming temporary calderas, while gases thicken the already volatile atmosphere. This is not a surface shaped by erosion or sediment, but by accumulation, by outpouring, inundation, repetition. The Earth remakes itself by covering its own skin again and again with heat. In these fire seas, the first plateaus form not through uplift but through persistence. Layer upon layer of cooled basalt rises incrementally, creating highlands, not of stone fractured by tectonics, but of stone poured spread and stacked in silence. Between the great flows, pyroclastic activity emerges. Ash clouds billow into the dense air, casting veils of particulate shadow across the glowing terrain. These eruptions are brief and fierce, and though their fragments do not travel far, they accumulate. In some areas, repeated explosive events create mounds of welded tuff, and volcanic breccia, the Earth's first dry hills, fragile and steep. From orbit, if the skies were clear enough to allow a view, the planet might resemble a scarred ember, its highlands smouldering, its lowlands awash in fire, its air shimmering with suspended minerals and acidic haze. Even now the crust is thin, but it is enough to carry weight. Enough to hold features for more than a moment. Mountains are still rare in the modern sense. There are no folded ranges, no colliding plates. But there are volcanoes, immense slow-growing towers of solid rock, layered from eruption after eruption, rising kilometers into the atmosphere, like slow exhalations of pressure. Yet none of this suggests permanence. The crust remains vulnerable to both internal disruption and external assault. Plumes from the mantle destabilize any region that thickens too much, while the tail end of the planetary bombardment still sends objects falling from above. Each impact is less frequent now, but when it comes, it can erase entire provinces. Still, the balance has shifted. The rate of creation exceeds the rate of destruction. For the first time, the Earth is building more than it loses. This is the beginning of surface memory, not yet history, but something like it. Volcanic provinces last long enough to define local geochemistry. Regional crustal domains begin to diverge in composition. A sense of difference of place is beginning to emerge. There is irony in the fire's repetition. Each eruption, each flow seems identical, molten basalt pouring from rift or vent, cooling into layered plains. But within those flows are slight variations in trace elements, in crystal formation, in gas content. These are the fingerprints of mantle dynamics, of subtle differences in melting regimes and source materials. What looks like sameness is rich with distinction. Only took a few 100 million years to realize the fire is never quite the same. Only took the repetition of lava flows across 1 billion years to etch the first notes of geology's music. Still, the process carries questions. Why do some volcanic provinces persist while others vanish? What controls the longevity of these fire seas? Is it the thickness of the crust, the chemistry of the mantle, or the rate of internal heat loss? Some scientists suggest that early superplumes, immense deep-rooted upwellings from the lower mantle, are responsible, delivering vast amounts of heat and melt to specific regions. Others point to crustal composition, arguing that regions with slight felsic enrichment resist subsidence and retain surface expression longer. The truth likely lies in the interplay between deep earth dynamics and surface feedbacks, a conversation between layers that we can observe only indirectly through the chemistry of rocks that have travelled long paths from formation to preservation, and yet through it all the Earth continues to build upward. Even without true mountain ranges, elevation exists. Layered flows harden into plateaus. Shield volcanoes rise to improbable heights. Some of these early edifices rival Olympus Mons in scale, though they will not survive into the modern age. Erosion is still minimal, there is no liquid water, no rivers to carry stone away, but gravity still pulls, and over time the steepest formations collapse their flanks, slumping in slow-motion avalanches. In these lands of fire, gravity is the first sculptor. It carves not with water or wind, but with weight. The atmosphere thickens further. Volcanic gases dominate carbon dioxide, water vapor, sulfur dioxide, and trace hydrochloric and hydrofluoric acids. The air remains unbreathable, but the addition of water vapor is crucial. It accumulates, it saturates, it weights. Some speculate that even now droplets may form in the highest, coolest reaches of the atmosphere, only to evaporate long before reaching the ground. Still, the process of cooling continues. Slowly, excruciatingly, the skies move toward condensation. The volcanic mountains and fire plains below may one day feel rain, but not yet. And in the silence between eruptions, something else stirs. Thermal inertia, crustal thickness. The Earth is gaining insulation. The surface, though volcanic, begins to hold heat in new ways. A thermal boundary layer emerges, not just a temperature gradient, but a shift in regime. The mantle must work harder to push heat to the surface. Convective cycles deepen. The upper mantle stratifies slightly. The planet is beginning to internalize its fire. No longer purely eruptive, the Earth now stores heat for longer intervals before releasing it in pulses. This rhythm will one day underpin tectonic's volcanism and the planet's long climate oscillations. But for now, it means longer pauses, deeper flows, and a surface that can briefly remember itself. In these seas of fire and mountains of ash, the Earth begins to rehearse stability. It is not there yet, but its eruptions are no longer random. They build, they layer, they return. And in those returns, a story begins not of life, not yet, but of place, of sequence of time made visible in stone. Far beneath the volcanic plains and the crust's brittle skin, the planet's deepest secret is already at work. In the outer core, a vast ocean of liquid iron alloy circling the solid inner core motion gives rise to something unseen but critical, a magnetic field. The geodynamo, driven by the slow spiraling currents of electrically conductive molten metal, awakens quietly with no surface sign, no light or sound. And yet it changes everything. The Earth is now wrapped in a bubble of influence, a magnetic shield that curves outward into space-bending solar particles and interstellar radiation around it like water around a stone. It is invisible, intangible, but real, and it is alive with motion. The mechanism is both simple and incomprehensible. As heat escapes from the solid inner core into the outer core, it drives convection, creating currents. The Earth's rotation then imparts a twist to those flows. Coriolis forces stretch and spiral them into helices. This movement of metal generates a magnetic field, which in turn reinforces the motion that created it. A feedback loop, quiet and powerful, begins. The planet generates its own magnetic environment, not passively but actively through its own internal heat and rotation. Fire makes this possible, but now it works in darkness. No longer erupting fire is organizing itself deeper, denser, unseen. Above, the magnetic field reaches out. It is not yet as strong or stable as it will become, but it is sufficient. Solar wind, a constant stream of charged particles from the young and volatile sun, now meets resistance. Instead of stripping away the upper atmosphere as it did and still does on Mars, the Earth's magnetic field deflects it. Charged particles spiral along the lines of force funneled toward the poles, where they may one day create auroras. For now they are simply repelled. The atmosphere, thick with volcanic gases and unbreathable as it is, gains a kind of protection. Loss slows. Retention begins. What little the planet has managed to accumulate it can now begin to keep, and yet this field, so consequential, is almost undetectable in the geological record. There are no magnetic signatures in rocks this early, no preserved orientations of iron minerals pointing toward ancient poles. The crust is still too young, too unstable, too molten. Rocks melt and remelt before they can lock in any memory of field direction. But the evidence is there in principle. The conditions for magnetism exist. The core has differentiated. The outer core remains fluid. The planet rotates. The field, though unmeasured, is inevitable. Only took a sphere of molten iron deciding to spiral. Only took the right amount of cooling at the right depth. Only took a planet turning in darkness to shape its own shield. Mysteries remain, as they always do. When exactly did the geodynamo begin? Some evidence points to an early start within a few 100 million years of Earth's formation. Other interpretations suggest it was intermittent, at first perhaps only truly stable after the inner core began to crystallize. What seeded the initial magnetic field, the first pulse that set the feedback loop in motion? Was it inherited from the solar nebula? Was it induced by large-scale impacts, or did it arise spontaneously from motion alone? These are questions without settled answers. We do not yet fully understand the birth of magnetism on Earth, only that once begun it became indispensable. And so the field hums. It has no sound, no light, no direct touch. But it becomes the quiet guardian of everything that follows. Without it, atmospheric escape would strip the planet's gases over time. Radiation would bombard the surface unfiltered. Water, if it formed, would be ionized and lost. Life, if it ever emerged, would be fragile in the extreme, but with it there is a buffer, a shelter, an unseen architecture of safety that stretches into the solar wind and says here there is resistance. There is something poetic in the idea that deep within the planet's darkest zone, beyond the reach of light, air, or stone, an invisible structure arises to defend the surface. Magnetism becomes the first signal of internal coherence of planetary systems, interacting across layers. The solid core cools the outer core, flows the mantle convex, and the crust begins to stabilize all parts of a single continuous choreography. The magnetic field is not a thing apart, but an expression of everything else working in unison. It is not an addition, but a consequence. On the surface, the changes are imperceptible. Volcanism continues. Lava flows still stretch for hundreds of kilometers. The atmosphere remains dense and acrid, thick with steam and sulfur. But now those gases linger longer. Less is lost to space. The planet begins to hoard. It begins to remember, not just in rock but in air. The atmosphere protected by magnetism will become a collaborator in the story of surface change. Not yet, but soon. Even in the deep earth, the geodynamo sets up patterns that will endure. The outer core's motion is not uniform. It pulses, swirls, shears. Over time, these flows will cause the field to wander, to reverse, to change intensity, but it will not disappear. Once ignited, the engine continues. Heat from the core powers it. Rotation organizes it, and time once again sustains it. The magnetic field is not a fixed structure. It is a process, an outcome, a symptom of deep motion that never ceases. In this it mirrors the planet itself, not still, not settled, but always becoming. The Earth now has more than a surface, more than a crust. It has a shield, not one made of stone, but of motion and force. It cannot be seen, it cannot be touched, but it will be felt, and one day it will make all the difference. Above the fire-scarred crust and beneath the protective arc of the newborn magnetic field, Earth's early atmosphere thickens into something more than haze. It is not breathable, not blue, not even consistent, but it is undeniably present. Composed of volcanic gases exhaled from the mantle's deepest recesses, it hangs heavy and opaque, a dome of chemical complexity suspended above a restless surface. Water vapor is the dominant presence, joined by carbon dioxide, sulfur, dioxide, methane, ammonia, and trace hydrochloric compounds. There is no oxygen yet, no ozone layer to filter the sun's ultraviolet light, and no ski as we know it, only a rolling ceiling of heat, darkness, and corrosion. The air burns the throat and blinds the eye, but it clings to the planet now dense enough, warm enough to resist escape. This early atmosphere is born not in calm, but in violence. Every volcanic eruption injects gases into it. Every impact stirs its composition. Every release of pressure or degassing magma plume modifies its chemistry. It is dynamic in the extreme, constantly thickening and thinning, varying in local density and composition, like a living exhalation of the planet's interior. There are no storms in the modern sense, no fronts, no pressure gradients moderated by oceanic currents. But turbulence still exists. The upper atmosphere is bombarded by ultraviolet radiation, which breaks apart molecules and ignites photochemical reactions. Ionized particles swirl along magnetic field lines, creating auroras invisible beneath the dense lower atmosphere. The entire sky pulses with chaotic energy, lit by frequent lightning discharges, that arc through the heavy vapours, each flash an expression of instability between earth and sky. And yet through this violent structure emerges. Layers begin to form. The densest gases settle near the surface while lighter compounds rise and accumulate above. This stratification is crude but meaningful, a first step toward atmospheric organization. Over time, thermal gradients develop, allowing the beginnings of circulation patterns. Convection within the atmosphere mirrors that of the mantle, hot gases rising, cooling slightly, then descending in slow loops. The sky moves, not with wind but with breath. Rain still cannot fall. The atmosphere is saturated with water vapor, but the temperature remains too high for condensation. Clouds may form at extreme altitudes only to evaporate before reaching denser layers. Some models suggest that high, above the planet's surface in the cold upper reaches of this proto-atmosphere, brief precipitation events may occur, droplets forming and vanishing mid-air, never reaching the ground. Even if they do survive part of the descent, they flash to steam upon contact with the searing crust. The cycle completes itself without effect, a rehearsal for hydrology still centuries away. And yet it is trying. Only took a few 100 million years for vapor to think about becoming liquid. Only took fire to slow just enough for water to dream of touching stone. This evolving atmosphere holds within it another quiet paradox. Though born of volcanism and trauma, it is also the cradle of cooling. Greenhouse gases trap heat, but they also enable the development of radiative equilibrium. As the atmosphere thickens, it begins to regulate the flow of thermal energy, not to halt it, but to control its rate of departure. A balance, however tenuous, is forming. The planet is still losing heat, still cooling. But now it does so through layers. Energy moves upwards slowly through strata of chemical complexity, rather than escaping freely into the vacuum of space. The Earth becomes less a glowing ember and more a simmering cauldron. And with this simmering comes retention. Volatiles that once would have escaped are now caught. Hydrogen still flees, it is too light, too fast, but heavier molecules remain. The Earth begins to keep what it exhales. Ammonia, methane, and carbon compounds collect. Sulfur compounds linger. Even early water vapor begins to saturate. The magnetic field helps deflecting charged solar particles that might otherwise strip these molecules away. Without it, the atmosphere might never have thickened at all. Mass smaller and magnetically quiet will one day illustrate what that loss looks like. But Earth, turbulent though it is beginning to hold itself together, and so the atmosphere becomes a system and engine of change. It is not yet stable, not even close, but it is engaged with the crust, with the mantle, with the sky. Every volcanic eruption alters its balance. Every new crustal fragment adds or absorbs gases. Even the sun, still young and volatile, influences its chemistry through solar flares and radiation. This feedback, chaotic and non-linear, is the earliest form of climate. Not climate in the sense of predictability or zones, but in the sense of sensitivity, of continuous negotiation between interior and exterior. The planet begins to feel its own surface. Uncertainties abound. What was the exact composition of this early atmosphere? How much methane did it contain, and what role did it play in thermal regulation? Did ammonia persist long enough to matter, or was it broken down by ultraviolet light? Did early clouds reflect enough sunlight to slow warming, or did their density enhance the greenhouse effect? These questions cannot be fully answered by ancient rocks alone. We reconstruct this era through models, through laboratory simulations, through comparative analysis with other planets. Venus, with its choking carbon dioxide atmosphere and sulfuric acid clouds, offers one vision of what Earth might have become. Titan Saturn's moon, shrouded in orange haze, suggests another. Earth's path was not inevitable. Its atmosphere could have gone many ways. Still here it is, dense layered volatile, a sky without colour, without air, without rain, but not without consequence. The gases it holds will soon interact with liquid water, with minerals, with light. Chemical pathways will open, reactions will begin. The first whispers of prebiotic chemistry are still far off, but the stage is being set. The air is no longer inert, it is charged with potential. And in its deepest layers near the surface the air grows heavy with water vapour. The crust cools ever so slightly. The clouds thicken. The temperature falls just enough in some places some of the time. There are moments, brief, isolated, almost unnoticeable, when droplets form and do not vanish, when vapour becomes water, when rain, true rain, begins to fall, the first real contact between sky and stone, quiet, rare, but real. By now the earth bears the slow exhaustion of a world no longer under siege. The final echoes of the late heavy bombardment are fading. What once was a constant rain of fire and stone now becomes a dwindling trickle. Impact events still occur, but their frequency has dropped precipitously. The sky is not empty, it never truly will be, but the threat from above has begun to wane. The inner solar system is settling its orbits, clearing its debris, either absorbed, ejected, or rendered inert. Earth, having absorbed billions of years of cosmic punishment, enters a new era, not of peace, but of relative quiet. The difference is not immediate, nor is it felt in any one place. It accumulates in absence, in the increasing intervals between devastation, in the silent growth of surfaces that are not immediately erased. Craters still form, but they begin to last longer. Their rims survive more than a single geological breath. Some are flooded by lava, others partially buried in ash, but a few persist long enough to begin shaping local topography. For the first time, surface features can endure. The Earth begins to host patterns. This is not stability in the modern sense, but a kind of reprieve. In the absence of continual bombardment, volcanic systems reorganize, tectonic patterns sharpen. The crust, though still thin and dynamic, becomes the primary medium of change, no longer merely reacting to external trauma, but responding to internal pressures and rhythms. The planet is turning inward. The forces that matter now rise from below, not fall from above. The reasons for this decline in impacts are not mysterious. The solar system has grown up. Planetesimals have been incorporated into planets, moons, and asteroids. The gravitational shuffle of the gas giants has settled. Resonances have emptied the corridors of chaos. The few remaining strays are swept up over hundreds of millions of years by persistent planetary gravity, or flung outward to the distant edges of the system. The inner worlds, once violently entangled, now drift in comparative quiet. Earth, lucky in mass and position, retains enough gravity to capture some of the debris, but not so much as to attract catastrophe. The Moon, too, plays its part, absorbing countless impacts and recording them in its unchanging crust. There the record remains, here it is overwritten, still uncertainties linger. Was the decline smooth, or did it come in waves? Some models suggest a sharp drop-off following the migration of Jupiter and Saturn, a gravitational reshuffling that cleared the inner solar system. Others propose a more gradual tapering, with clusters of impacts tied to specific orbital disruptions. The lack of surviving ancient crust on Earth leaves much of this unresolved. We look instead to the Moon, to Mars, to meteorites, fragments of the past that preserve what Earth has lost. Yet even with this uncertainty, the trend is clear. Fewer impacts, longer intervals, more room for Earth's internal processes to take the lead. And with this shift, the surface breathes differently. The crust begins to spread and thicken in places. In others, it fractures and founders. Subduction is not yet global, but local downwellings become more common, especially where cooled lithosphere sinks beneath younger, hotter flows. These zones of recycling grow in number, forming primitive tectonic corridors. They do not yet resemble modern plate boundaries, but they begin to show preference regions where heat escapes more efficiently, where magma rises more frequently, where old crust disappears into the mantle. From the patterns of convection, from the scars of past impacts, from the long conversation between fire and stone, a new logic begins to emerge. Above all this, the atmosphere stabilizes incrementally. The absence of large impacts means fewer sudden injections of dust and vapor. Climate swings moderate. Volcanism still pulses, but its effects are regional, not planetary. Steam clouds still rise, but they are no longer joined by the ashen debris of extraterrestrial collision. The sky, though thick and unbreathable, becomes calmer. Radiative cooling becomes more consistent. Temperatures drop not dramatically but measurably, and with them the potential for condensation increases. In some areas, water begins to persist on the surface, not in brief rivulets that evaporate within seconds, but in shallow pools. These puddles gather in impact basins and volcanic depressions. They do not yet form oceans, but they stay. This persistence matters. Water, once it touches stone, begins to react. It weathers minerals, alters surfaces, dissolves ions. These chemical interactions are slow, but they begin the vast cycle of sediment and solution that will eventually shape all life. The early Earth, still hostile and hot, is now touched by chemistry in motion, not just molten transformation, but aqueous exchange. Every drop that stays marks a quiet revolution. Only took a few billion years for a rock to hold water. Only took the sky to stop falling long enough for the crust to hold firm. Only took the violence to ebb before gentler forces could begin their work. Even so, the transition is not absolute. Impacts continue. Some are large. Occasionally a crater disrupts an entire volcanic province or triggers a global atmospheric response. But these events are rare, exceptional. They do not define the epoch. What defines it now is duration, the increasing stretch of uninterrupted time between catastrophes. That time is what allows crust to grow basins, to form gases, to accumulate, and water to linger. It is what enables the Earth to begin becoming itself, not in reaction to violence, but in the slow assertion of its own inner systems. From this point on, the story of the planet shifts. The bombardment which once dictated every surface detail now retreats to the margins. It becomes a background process, not the headline. The crust, the mantle, the atmosphere, they are now the main actors, and through them Earth will enter a new phase of complexity. It will try tectonics, it will hold oceans, it will host cycles of carbon and sulfur, and eventually it will welcome life. But first it must learn to keep quiet. Beneath the cooling crust, the mantle churns onward, quiet, vast and unrelenting. Its convective cells deepen and stabilize, slowly shaping the surface from below in patterns no eye can see. There are no continents yet, no familiar outlines, no fixed plates shifting across the globe. But already fragments of crust are in motion. Slabs formed from cooled volcanic flows and stabilized by local pressure balances begin to drift laterally, carried by the creeping movements of the lithosphere riding atop the asthenospheric tide. This is not plate tectonics in the modern sense. It is uncoordinated, inconsistent, fragile. There are no long-term boundaries, no preserved records of collisions, no crustal roots deep enough to anchor identity. Yet still the pieces move, pushed from below, pulled from above, dissolved, consumed, replaced. Tectonic drift begins not with permanence, but with forgetting. These early motions are erratic. Small fragments of crust, sometimes called protocontinents or terranes, glide over the mantle for a time, before being broken apart by rising plumes, or pulled downward into hotter regions where they melt and are recycled. The subduction is shallow, inconsistent, governed more by thermal contrast than structural logic. There are no trenches or island arcs, yet only zones where colder, denser slabs slip below warmer regions and vanish. Surface features appear and disappear within millions of years, eroded not by weather but by fire. What the Earth creates, it still consumes quickly. No mountains survive, no basins hold sediment, there are no witnesses to remember where anything was. Each crustal experiment is a solitary note quickly absorbed into the deeper chord of mantle flow, and yet these drifting fragments leave faint geochemical traces. In the isotopic signatures of ancient rocks, samarium and neodymium, hafnium and zirconium scientists detect the echoes of early recycling of crust that formed, changed and re-entered the mantle. Some of these clues persist in modern continental shields in the deepest parts of the oldest rocks, where remnants of early crust barely recognizable have survived eons of transformation. They tell of a time when the surface was restless in a different way, not fractured into clean plates, but constantly remade with no memory from one cycle to the next. The Earth was moving but not yet recording. There is irony in this amnesia. The processes that allow tectonics to eventually become predictable crustal thickness, density, contrast, water-assisted melting are already beginning here. But without stable continental roots, without a consistent lithosphere, the movement remains impermanent. The planet is laying the groundwork for its own geological memory, but it cannot yet remember itself. Only took a few 100 million years for plates to move. Only took another billion for them to leave a mark. Why did this early drift fail to preserve its history? Why is so little of Hadean and early Archean crust still with us? The answers lie in the interplay of temperature and time. The early mantle is hotter, more turbulent, more chemically active. Crustal fragments are thinner, more mafic, more easily melted. Without water cycles to stabilize surface temperatures, and without significant erosion to create sediments, early crustal rocks are more exposed to thermal recycling. Even when slabs subduct, they do not sink into deep trenches with sediment blankets, they simply melt and mix with the convecting mantle. It is a system in motion, but not yet in memory. A planet experimenting with mobility but not with permanence. Still movement matters. The drifting of these fragments, even if ephemeral, redistributes heat. It helps the mantle regulate temperature gradients. It creates local zones of chemical differentiation. In areas where multiple fragments converge or overlap, thicker crust may form the earlier seeds of what will become continental nuclei. In others, upwelling plumes reset the landscape, pouring out new basaltic flows that start the cycle again. The planet is restless, not directionless. Beneath the apparent chaos lies a rhythm. The atmosphere responds. With fewer impacts from above, the gases accumulating in the sky now reflect surface processes more closely. Outgassing from volcanic ridges, rifts and subduction zones begins to dominate. Each drifting fragment acts as a temporary node of volcanic expression, contributing water vapor, carbon dioxide and sulfur compounds to the air. As crustal blocks form and vanish, they subtly alter the atmospheric composition. Cooling continues. Condensation events become more common, though still isolated. In low-lying areas, particularly those ringed by cooled lava water, may persist in pools for thousands of years. The water is acidic, mineral-rich and unstable, but it marks the first interaction between long-term crustal motion and surface hydrology. Meanwhile, the magnetic field born earlier in the core's convection continues to protect this evolving system. Though not yet stable in polarity, its presence deflects enough solar wind to preserve atmospheric volatiles. This interplay between deep earth and sky, between core and atmosphere, becomes more integrated. The planet is beginning to function as a system, not just a set of independent layers. The drifting crust, the flowing mantle, the shield of magnetism and the dense vaporous sky are no longer just coexisting. They're beginning to interact, to influence, to respond. The mystery persists. When did true plate tectonics begin? Was it a sudden transition, a threshold crossed when crust became thick and cool enough to sink in coherent slabs? Or was it gradual, a slow evolution from fragmentary drift to boundary-driven movement? The geological record offers no clear answer. Some argue for a tectonic onset as early as 3.8 billion years ago. Others suggest it emerged much later, around 3 billion. The evidence is ambiguous. The rocks too altered, too remade. What is clear is that this period marks a turning. The Earth is trying to remember, not yet successfully, but with increasing clarity. The crust drifts not aimlessly, but toward a future where its motions will leave scars. And so the surface changes again, not dramatically, not permanently, but noticeably. New crust forms in patches, old crust vanishes beneath it, basins appear, deepen, collapse, rifts open, volcanic arcs form briefly, then dissolve. There is no continent, no ocean, no fixed direction. But there is motion, and motion given time becomes memory. Among the drifting shards of ancient crust, certain regions begin to resist destruction. They are small, geochemically distinct, slightly less dense, and enriched with lighter elements, aluminum, silicon, potassium. These differences give them just enough buoyancy to avoid easy recycling into the mantle. With time, these patches of crust grow thicker, more stable, more resistant to thermal erosion. They do not yet resemble modern continents in size or structure, but they persist. And in a world of endless resurfacing, persistence is everything. These early survivors are the protocontinent's quiet bulges of felsic crust that begin to break the symmetry of the planet's volcanic plains. Their emergence is not dramatic. There are no mountain chains or continental shelves, no rivers or soils, but they change the rules. They're cooler than the surrounding mafic crust, and they insulate the mantle below, altering convective patterns and redirecting upwelling plumes. Their presence modifies volcanism, producing more silicic lavas in places, and subtly altering the chemistry of the atmosphere through changes in outgassed volatiles. These protocontinents also begin to collect what little sediment the young world can produce, chemical precipitates, volcanic ash particles of weathered rock carried by wind or temporary water. In shallow depressions, these materials accumulate in thin layers, embedding the earliest traces of environmental variation within a framework that can finally endure. The mechanisms that allow protocontinents to form are still debated. Some theories suggest that mantle plumes melt older basaltic crust to produce lighter granitic material. Others argue that early subduction zones, however primitive, generate the pressure and temperature conditions necessary for partial melting and felsic differentiation. Perhaps both are true at different times and in different places. What matters is that some regions of crust now survive longer than others, not just geologically but thermally and chemically. These patches do not merely float. They shape the future flow of energy across the planet's surface. Their resilience brings irony. These are not the largest or most volcanically active areas. They do not host the tallest peaks or the widest lava flows, but because they survive, they become the bedrock of history. Later supercontinents will stitch themselves around them. Rivers and weather systems will erode their surfaces. Life, once it emerges, will take root in their margins. But for now they simply endure silent, heat-blunted fragments of a planet beginning to define its face. Even in this endurance, the protocontinents remain vulnerable. The mantle is still warm, still dynamic. Basaltic underplating threatens to remelt the base of their crust. Collisions with other fragments can thicken or shatter them, but their survival rate begins to climb. In some cases they merge with nearby fragments, forming composite terrain zones of slightly thicker older crust, patchwork together through collision and magmatic intrusion. These proto-assemblages create regions of slightly higher elevation enough to redirect surface water to collect weathered material to alter localized climate patterns. The planet is beginning to show texture. Still, the Earth does not remember these early landmasses in their original form. Most have been deeply metamorphosed, intruded by later magmas, or buried beneath more recent strata. What remains are the ancient cratons' core blocks of stable continental lithosphere preserved through billions of years. Places like the Cape Vale in southern Africa, the Pilbara in Australia, the Canadian Shield, these are the distant echoes of protocontinents, their identities reshaped but not erased. Their cores preserve zircon's more than 4 billion years old mineral time capsules that record the pressure, temperature, and isotopic environment of their birth. In their chemistry lies the memory of this quiet continental dawn, and yet their birth is only part of the story. Once established, these protocontinents begin to influence everything around them. They stabilize local mantle convection, creating zones where upwelling is suppressed and downwelling becomes focused. They deflect volcanic activity to their margins. They cool the mantle locally, making it more viscous and less prone to resurfacing. In essence, they reinforce their own survival. This feedback loop is slow but effective. Only took a few dozen degrees of temperature difference to create a stable surface. Only took patches of granitic crust to resist 4 billion years of fire. Above the atmosphere continues its evolution. The declining frequency of impacts, the stabilization of crust, and the persistence of highlands all contribute to a more layered climate system. Clouds form more consistently. Rain, though acidic and transient, begins to fall with regularity in some places. Water collects in depressions, impact basins, volcanic calderas, rift valleys forming ephemeral lakes or long-lasting pools depending on local conditions. On the protocontinents, these water bodies begin to interact with minerals in the crust, generating clays and altering basalt into serpentine and other hydrated rocks. The planet's surface is slowly shifting from a fire-dominated world to one sculpted by water and time. These interactions open new pathways in geochemistry. Weathering begins to draw down atmospheric carbon dioxide, sequestering it in carbonate minerals and organic precursors. Silicate rocks exposed to rainfall and runoff begin the long, slow cycle that will eventually regulate climate. The Earth is building a thermostat, not consciously and not deliberately, but through chemistry and repetition. The protocontinents provide the scaffolding for this process. They are the anchors that allow water to linger, elements to cycle, systems to feed back upon themselves. The mystery remains: why here and why now? Why did protocontinents emerge when they did, and why did they succeed in some places but not others? The answers are locked in mineral textures, isotope ratios, rare inclusions preserved under impossible conditions. Geologists find clues in detrital zircons, in ancient tonalites, and gneisses in high-pressure minerals preserved in the hearts of metamorphic belts. But the story is incomplete. The early Earth does not tell its secrets easily. It whispers them from beneath layers of recrystallized rock and eons of overprinting. Still, we know enough to see the outline of emergence, a planet beginning to shape a surface that could last. And so the protocontinents rise not like islands thrust upward, but like embers too dense to be extinguished. They do not seek dominance, only endurance. The planet does not yet recognize them as special. But time will prove otherwise. In the deepening quiet between bombardments, beneath a thickening sky, and atop a crust that no longer melts as quickly as it forms, water begins to gather. Not as vapor suspended endlessly in the atmosphere, not as transient droplets vanishing on contact with fire, but as true liquid, cool enough to persist, heavy enough to stay. It seeps into the lowest places, pools in volcanic basins, and impact craters, runs in channels carved by gravity and time. This is not the blue water of later ages, not yet ocean or river, but a thin, dark film of mineral-rich liquid that coats the young Earth's uneven skin. The surface, once a place of only fire and fracture, now glistens in parts. For the first time, Earth begins to shine not just with light, but with reflection. The process is slow conditional, easily reversed. A major eruption or large impact can still vaporize entire regions, turning lakes to steam and skies to ash. But over time the balance shifts. Cooling outpaces heating. Condensation begins to exceed evaporation. The atmosphere, still hot and dense, starts to act as a lid rather than a furnace. As more water vapor condenses into liquid, the climate stabilizes in stages. Acidic rains fall, weathering the earliest rocks, releasing ions that flow back into these primitive basins. Chemistry begins to stir. Water's interaction with stone is immediate and irreversible. Basalts absorb it, crack, transform. Feldspars break down into clays. Ions of calcium, magnesium, sodium, and potassium are drawn into solution, beginning the long process of differentiation between crust and ocean. In some basins, carbon dioxide dissolves, forming weak carbonic acid that etches into exposed surfaces. These reactions lower the albedo of the land, changing how the planet reflects sunlight, feeding back into the temperature regulation that allows water to remain. Fire shaped the early Earth, but water now begins to alter its memory. The earliest accumulations are shallow ephemerals scattered across regions shaped by topography too young to have direction. But they mark a fundamental change in the planet's behavior. Heat alone is no longer the sole sculptor. Liquid water, persistent and reactive, takes up the task of rearrangement. It carves, dissolves deposits. It initiates erosion even without life or plants or sediment. With each rainfall, with each flow, the surface becomes less volcanic and more chemical. Not all at once, not everywhere, but the shift begins. And in this quiet shift lies a suite of emerging paradoxes. The atmosphere filled with greenhouse gases is both hot and wet conditions that promote surface water while also threatening to boil it away. The magnetic field, invisible and undetected at the time, quietly protects these early pools from solar stripping. The protocontinents, sparse and fragmentary, provide just enough high ground for runoff and basin formation, and the mantle, still active, continues to feed the process through volcanism that adds water and gases, but now at a rate that no longer overwhelms the planet's ability to cool. Only took 1 billion years for heat to step back. Only took a few 100 million more for water to take its place. The sources of this water are layered in uncertainty. Some comes from degassing of the mantle hydrogen and oxygen released in early magmas and recombined into liquid as the surface cooled. Some may have arrived through impact from icy planetesimals, remnants of the solar system's distant past. Isotopic analyses suggest a mix of both hydrogen signatures that align partly with Earth's own rocks and partly with carbonaceous chondrites, those ancient messengers from the outer solar system. The truth is not singular. Earth's water is not from here and also very much from here. It is both inherited and earned. Once present, water begins to mediate nearly every surface process. The rock cycle expands erosion, transport, chemical weathering, precipitation of minerals in evaporative basins. Hydrothermal systems flourish near volcanic zones, circulating through cracks and faults, leaching elements from deep rock and depositing them elsewhere. These systems, driven by heat and moderated by water, create pockets of concentrated chemistry, places where minerals interact in new ways, where gradients of temperature and pH form natural laboratories. Life does not yet stir, but the preconditions for complexity are multiplying. With every drop of persistent liquid, the Earth becomes more than a sphere of stone. Still, the oceans are not yet here. The water that exists is mostly trapped in basins and lakes, perhaps spreading across broader lowlands in thin sheets during heavy rainfall. Evaporation is still high. Volcanic eruptions still reset the landscape frequently, but these pools endure longer with each passing cycle. They accumulate solutes. They begin to stratify. Surface tension draws patterns in their skins. Waves the faint ripple across their surfaces, driven by wind that is only just beginning to stabilize in direction and force. The idea of water as a constant presence becomes more than a hope. It becomes a fact. The growing presence of water also begins to challenge the crust in new ways. Saturated rocks are more prone to alteration. Some become unstable, slumping into nearby basins or collapsing into sinkholes. In areas of high geothermal gradient, water interacts with magma to create explosive eruptions, phreatomagmatic events that send ash high into the air and dig Mars into the crust. These are localized disasters in a time before life, but they leave behind new structures, crater lakes, hydrothermal fields, altered rocks that will one day host ore deposits. The earth in growing wetter becomes more dynamic. Fire does not disappear. It changes its language. The evidence for these earliest waters survives not in fossils or deltas, but in minerals. Ancient zircons once crystallized in cooling magmas show oxygen isotope ratios that suggest interaction with liquid water as early as 4.3 billion years ago. These tiny crystals, older than any rock, preserve an invisible history of steam rain and runoff. Later sediments metamorphosed, folded, buried, contain banded iron formations and carbonates that reflect conditions in water-rich environments. These clues are sparse, scattered, ambiguous, but taken together they form a whisper, one that grows louder as the Hadean fades into the Archean, and so the surface changes again. Not with a sudden flood or global ocean, but with quiet, persistent pooling. Water finds the low places and waits. It soaks into rock flows between grains, evaporates and returns. It begins to write its own story, not in lava or impact melt, but in dissolution and deposition. And in that story lies the outline of everything that will follow. For with water comes cycles, with cycles comes chemistry, and with chemistry and time comes life. As water spreads and carves, fire learns restraint. The earth once ruled entirely by heat begins to reorganize that power, driving it inward, refining its expression. Volcanism does not vanish. It becomes rhythmical, less global, more focused. Instead of flooding the entire surface in lava seas, eruptions localize into arcs, rift zones, and hotspots. The mantle is cooler now, still convecting, but with narrower thermal gradients, its plumes more predictable, its output more moderated. Crust once instantly obliterated by molten tides now survives long enough to fracture and heal, thicken and thin, migrate and respond. The heat beneath still pulses, but it no longer dictates everything. It negotiates. This change is structural. The crust has grown thicker in places, especially where early protocontinents have formed and merged. These buoyant masses of felsic rock act as shields insulating the mantle and altering the flow of heat upward. Basins between them host cooling lava plains and shallow seas. Volcanic activity shifts to their margins, where the contrast between thin and thick crust triggers localized melting. Subduction, still primitive, becomes more coherent, carving deepening trenches and forcing hydrated rock into the mantle, where it releases water and lowers the melting point of the surrounding rock. The cycle feeds itself. Fire withdraws from the center of things but finds new potency at the edges. This withdrawal does not signal decline, it marks evolution. The Earth is not cooling into quiet but into complexity. Volcanic systems become more diverse. Some erupt basaltic flows, fluid and dark, spreading across the lowlands in gentle sheets. Others, richer in silica and volatiles, erupt explosively, sending ash and pumice into the atmosphere, creating transient darkness and acid rains. Caldera formation begins in earnest, leaving behind collapse basins that fill with water and become chemical laboratories. Fumaroles hiss, geysers erupt. Hydrothermal systems lace the surface, tracing the plumbing of an inner world still deeply alive. The planet does not sleep. It dreams in steam. Even in its restraint, fire remains everywhere. Beneath the crust, the mantle still rises and falls in great convective loops. In the core, the geodynamo still turns, powering the magnetic shield that protects the upper atmosphere. Along rift zones, new crust forms as lithosphere splits and magma intrudes, rebuilding the seafloor in miniature before it even has a chance to be called that. Volcanoes now exist in chain-like arrangements, rising above subduction zones or trailing behind migrating plumes. The heat is less overwhelming but more targeted. It becomes a sculptor, no longer a flood. Evidence for this shift can be found in ancient greenstone belts, strips of metamorphosed volcanic and sedimentary rock that record the interaction between early crustal fragments and volcanic processes. These belts, often nestled between more stable continental cores, preserve sequences of pillow lavas, ash layers, banded iron formations, and chert, all pointing to a world in which fire and water coexist. They show that volcanoes now erupt into shallow seas that lava cools beneath water, into rounded forms that sediments accumulate between flows, binding the episodic with the enduring. It is in these rocks that fire's retreat becomes visible, not as absence, but as integration. And with this integration come new feedbacks. Volcanic outgassing still drives atmospheric chemistry, but the presence of standing water now alters how gases circulate and react. Carbon dioxide dissolves, forming carbonic acid that weathers rocks, drawing down greenhouse gases and feeding the slow cooling trend. Sulfur gases interact with water to form sulfate aerosols affecting albedo and climate. Even the explosive force of eruptions is tempered by interaction with water flash boiling causes fragmentation, while undersea eruptions are muffled and build rather than destroy. Fire, once sovereign, is now part of a network. The biosphere has not yet begun. Life remains absent or undetectable, but the stage is nearly ready. Nutrients phosphorus, nitrogen, sulfur ion are being cycled between magma atmosphere and water. Clay minerals form in hydrothermal systems, their layered structures ideal for concentrating organic molecules. Heat gradients near volcanic vents offer niches of stability and flux, the kind of conditions that favor chemical evolution. If life is to begin, it will likely start here at the intersection of fire's legacy and water's persistence. Still, there are uncertainties. How uniform was this shift? Did all parts of the Earth evolve at the same rate? Or did protocontinents host calm while other regions still erupted wildly? Were early subduction zones truly global or confined to specific domains? How deeply did water penetrate the crust, and how consistently did it interact with the mantle? The geological record offers clues but no full answers. Much has been overwritten, metamorphosed, eroded, or lost. Yet the patterns that survive suggest a planet in transition, a world testing the boundaries of its own systems, finding a new equilibrium through oscillation rather than stasis. Only took 2 billion years for fire to make room. Only took 100 million more for water to respond. Only took a planet's unwillingness to stay uniform for complexity to arise. Fire still rules beneath the surface. It fuels the tectonic engine, the geodynamo, the venting of gases that keep the sky in balance. But it no longer commands alone. Its retreat is not defeat. It is refinement. And so the Earth becomes something new, not a sphere of fire, not yet a cradle of life, but a place where elements balance and reshape one another. A planet where fire flows beneath and water pools above, where crust drifts and reforms, where gases cycle, where stone remembers heat but begins to host cold, where the old dominance of eruption is slowly replaced by the long dialogue of systems. Fire is not gone. It waits patient and essential beneath the crust, ready when needed to remind the surface of its origin. Beneath the quieted surface, fire continues hidden, reshaped, yet utterly vital. The outer skin of the Earth, now a patchwork of protocontinents and volcanic plains, drifts slowly atop a still simmering mantle. The vast upwellings and downwellings of heat, once unrestrained and cataclysmic, now form persistent currents. They pull on the lithosphere, stretch it, fracture it, drag crustal fragments across the globe in slow, deliberate paths. The energy that once erupted unceasingly through every fracture now focuses its expression. The mantle is no less powerful than before, but its fire has been pulled inward, buried beneath the stabilizing weight of structure, and taught to move through constraint. In this hidden state, fire becomes function. It fuels the tectonic engine, generating new crust at mid-ocean ridges and consuming old slabs in subduction zones. It maintains the convection loops that circulate heat from core to surface and back again. It creates the pressure and temperature conditions necessary for mineral transformation, for magma generation, for metamorphic renewal. It powers hydrothermal systems that churn through rock, altering its chemistry, drawing nutrients into solution, returning them to the surface. Even as it withdraws from visibility, fire holds the Earth together. The crust may float, fracture, and collide, but the mantle breathes beneath it, steady and slow. The continents, still small and fragmented, continue to coalesce. Some merge through collision, thickening the crust and raising broad plateaus. Others remain isolated, drifting through ancient seas. Their cores cooled just enough to resist remelting, preserve geochemical signatures of the early Earth. Radiogenic isotopes locked into zircon grains record time in atoms. These records show that fire has never truly stopped. It has simply learned to pulse. Volcanism, once universal, now occurs in belts. Subduction zones form long arcs of composite volcanoes, where oceanic lithosphere dives beneath buoyant fragments. Mantle plumes rise sporadically, forming volcanic islands that trace the paths of moving plates. The Earth is now a planet of cycles. Above, the atmosphere remains thick, but its composition shifts. Carbon dioxide, drawn down by weathering and incorporated into carbonate rocks, decreases in concentration. Water vapor, once overwhelming, now circulates through a growing hydrosphere. Rain falls regularly. Rivers etch into the land. Lakes persist. Evaporation, condensation, precipitation. These processes form the earliest true water cycles, exchanging energy and matter between earth and sky. And beneath the surface, groundwater moves through porous rock, reacting with minerals, aiding in metamorphism and heat transport. The presence of liquid water enhances fire's underground work, allowing it to flow not just through temperature but through chemistry. The magnetic field, still generated by convection in the liquid outer core, remains active and strong. It guards the atmosphere, allowing volatiles to accumulate rather than be stripped away by solar wind. Its invisible presence shapes auroras, protects molecules, stabilizes climate. In its silence, it ensures continuity. Without it, even the fire beneath the crust would eventually lose its purpose as the planet's energy balance unraveled. But with it, a shield remains. Not infallible, but enduring. And so the Earth begins to resemble something closer to the world we know, not in appearance, but in behavior. Systems interact, feedback stabilize, the cycles of rock, water, atmosphere, and magnetism align in rhythm. The great oxidizing event has not yet come. Life has not yet taken hold, but the ground is prepared. Oceans have begun to form from the merging of countless lakes and shallow seas. The first basins capable of holding them now exist, carved between drifting protocontinents and rising volcanic ridges. Their surfaces ripple with wind. Their floors accumulate sediments. Their chemistry reflects the input of volcanic gases, weathered minerals, hydrothermal fluids. They are turbulent, acidic, unpredictable, but they are stable enough to remain. And within them, fire's presence persists. Seafloor volcanism continues at spreading centers. Black smokers and alkaline vents rise from the deep, spewing, mineral-rich water into the surrounding sea. These hydrothermal systems, fueled by heat from below, create chemical gradients differences in temperature, pH, and redox state that form the first plausible niches for prebiotic chemistry. Organic molecules synthesized abiotically in the presence of catalytic surfaces begin to assemble into complexity. No cells yet, no replication, but building blocks. Fire filtered through mantle convection and crustal plumbing becomes a midwife to possibility. The irony endures: the same fire that once made the planet uninhabitable now creates the conditions for life. The same heat that erased early crust now drives the cycles that sustain water, atmosphere, and chemistry. Fire has not vanished. It has moved underground, waiting patiently, no longer dominant but indispensable. Only took 4 billion years for heat to learn subtlety. Only took continents to float and waters to fall for fire to find its quiet role. Above all, the Earth is now a world in balance, not of peace but of processes aligned. The mantle churns, the crust drifts, water circulates, the sky evolves, and deep beneath it all the core turns, feeding a magnetic heartbeat that pulses unseen. Fire, though hidden, touches every layer. It moves through subduction zones and upwelling plumes. It powers weather through geothermal gradients. It shapes mineral veins in deep rock. Its embers are everywhere, not gone, just quiet. This is the end of fire's dominance, but not its disappearance. It has not been defeated by water or crust or atmosphere. It has simply learned its place in the whole, and in that place it remains. Always ready to rise again should the balance break. Always moving even when unseen. Always warm beneath the surface. The Earth is no longer ruled by fire, but fire still breathes just below the crust, steady as time. The crust now holds steady beneath slow-drifting clouds. What once was a molten sphere of chaos breathes in long rhythms. Oceans, still restless, begin to find their shapes. Winds move more softly across the surface, tracing the curvature of a planet that has quieted just enough to remember its own weight. No longer ruled by fire, no longer silenced by stone, the Earth has entered an era of balance, precarious shifting, but real. Beneath the calm heat still rises, not as flood or flame, but as a murmur from the mantle, as a gentle exhale through hydrothermal vents, as a tremor that rolls through the ancient roots of newborn continents. The core turns slowly. The field hums without sound. Magma flows where needed, reshaping the deep without disturbing the surface. Fire, now buried, remains faithful. In the shallow seas, minerals settle into fine layers. In the warm tide pools near volcanic arcs, bubbles rise without direction. The chemistry of water deepens, enriched by the memory of rain rock and gas. The sky holds its weight without bursting. The crust bends but does not break. Earth for the first time becomes a place where time can stretch out, where change can unfold not in eruptions or impacts but in cycles, soft, long, continuous. And so the planet rests, not in stillness but in readiness. All the systems that will one day host life are in motion, tuned to one another in silence. Fire waits beneath, water drapes above, rock carries memory, air holds breath. The Earth turns slowly, quietly, an ember wrapped in ocean, wrapped in sky.